Okay, so today I would like to start with the second part of this course, which will be about coordination chemistry. So what we will do from now is applying the basic concepts that we have learned in the first part of the course to coordination chemistry in order to better understand coordination chemistry. So in the beginning, I would like to give a brief introduction into coordination chemistry. So what is coordination chemistry and what are coordination compounds? So generally we can consider coordination compounds, or as we can also call them complexes, as Lewis acid-base adducts in which the metals are the acceptors and in which the ligands are the donors. So coordination compounds and complexes are actually known since a long time, and they have sparked the interest of chemists also from very early on, because many of them have intense colors. So you see here 3 examples. So here we have copper sulfate, pentahydrate, which has an intense, beautiful blue color. So here we have iron trichloride hexahydrate, which has an intense yellow color. And over there we have nickel sulfate hexahydrate, which has a very nice blue-green color. So of course, chemists are interested, well, what is the chemical composition of these compounds and what is the bonding in these compounds? And very early on, chemists found, well, these kind of compounds seem to be more complex with regard to their bonding than other compounds, hence they're also called complexes. And the basic problem was that in the early days of chemistry, it was believed that the coordination number would not be able to exceed the valence of the respective metals. So, for instance, it was difficult to explain a compound like, as we call it today, hexamine cobalt chloride. So we have 1 cobalt, which is in the oxidation state +3 and has the valence 3, but we have 6 amine units and we have 6 chloro units. So according to what was accepted at the time, the cobalt could make only 3 bonds. So how can we have actually 3 chlorines and 6 units of ammonia in that molecule when we only have the possibility to make 3 bonds? And the first one who interpreted the bonding situation of coordination compounds correctly was Alfred Werner, who received the Nobel Prize for his work in the year 1913. So he actually broke with this belief that the number of bonds could not exceed the valence of the metal, and say this is possible, and we can have so-called complex ion in which we have 2 coordination spheres. The first coordination sphere in which ligands would be bound directly to the metal, and a second coordination sphere where the remaining constituents of the compound could exist to balance charges, but would not be bound directly to the metal. Okay, so he proposed that we can have larger coordination numbers at the metal, and we have primary and secondary coordination spheres. Okay, so let us in the next step briefly go through how we can name coordination compounds, because it is important that we can talk about coordination compounds in an educated way. So first of all, let's look at the formula writing. So because we have inner coordination spheres and outer coordination spheres, we place everything which is in the first coordination sphere, inner coordination sphere, in brackets, and write everything which is outside of that inner coordination sphere, outside of these brackets. So when we have a complex cation, then we write the formula for the complex cation first, and then the anion in the second coordination sphere behind, and if we have coordination compound which is a complex anion, then we first write the counter ion, in this case here the potassium, and the complex anion after that. So if we want to write out the explicit structural formulas, we could write the complex cation and the complex anion is shown here. So we could write the cobalt in the center with 6 amine ligands making 6 nitrogen cobalt bonds, or as shown over here, we could write here the iron in the center, whereby the iron would make 6 carbon nitrogen bond as 6 cyano-ligands are being bound to the carbon. So we do not want to write out the whole structure explicitly. We can also write the formula like this here. We can write the cobalt and the ligands, and then name the number of ligands and place the brackets around, followed by the formula for the chlorine. And over here we would write the potassium first, and then the iron and 6 cyano-ligands, where we again would put a brackets around the complex anion. Okay, so let us have a closer look at the ligands that can be in coordination compound and see how we can classify them and how we can name them before we actually try to name entire coordination compounds. So first of all, we can decide between what is called monodentate ligands and multidentate ligands. So when we have monodentate ligands, as the name says, there is only one donor atom at this ligand, and therefore there is only one point of attachment between the metal ion and the respective ligand. So monodentate ligands are, for instance, aqua ligands, H2O, amine ligands, NH3, and chloroligands, Cl-. So in the aqua ligand, the oxygen atom would be the donor atom. In the amine ligand, the nitrogen would be the donor atom. In the chloroligand, well, of course, the chlorine would be the donor atom, and one electron lone pair at the chloride anion would be donated to the metal. However, there would only be one point of attachment between these ligands and the metal. All right. Then, in contrast to monodentate ligands, we can also have multidentate ligands, which are also called chelating ligands, coming from the Greek word chela, meaning the great claw. And in the case of multidentate ligands, we typically have 2 or more points of attachments between the metal and the ligand, and these multidentate ligands then have also multiple donor atoms. So we indicate how many points of attachments there are by Greek prefixes. So for instance, when we have bidentate ligand with 2 donor atoms, we add the prefix di. When we have 3 donor atoms with 3 points attachment, 3 points of attachment, then use the prefix tri. When we have 4, then we use the prefix tetra. When we have 5, we use the prefix penta, and when we have 6, we use the prefix hexa, and so on. So let us look at a few multidentate ligands and see what they typically have in common. But before we do that, I just wanted to illustrate what chelate complex means. And I said already that it comes from the word chela, which means the great claw of the lobster. So why are these called chelate complexes? This is because these multidentate ligands, they hold the metal ions between their donating atom, like lobster would hold something with its great claws. Okay, but now let's look at what chelating ligands we have. There are many, and I'm just discussing a few of them. I would like you to know these few ligands that we are discussing in class. And I also would like you to know the typical abbreviations for these ligands that you often use in the in the formulas. So let's start with bidentate ligands. So one very common ligand is the ethylene diamine ligand, abbreviated with the letters En in parentheses. So in this case, we have two NH2 groups with two N donor atoms that are bridged by an ethylene group. So what else do we have? Another common bidentate ligand is the oxalate ligand. So in this case, we have two oxygen donor atoms with two carbon atoms in between. So another very common bidentate ligand is the bipyridal ligand. The abbreviation is bipyr. So this is kind of the aromatic analog of the ethylene diamine ligand. So again, we have here the nitrogens between two carbon atoms, but these two nitrogen atoms are now part of two pyridyl rings. So last but not least, here is the acetyl acetonate ligand. So again, we have oxygen donor atoms again. So in this case, we have here a keto group, here a deprotonate alcohol group, and three carbon atoms in between the two oxygen atoms and a double bond. So we can draw resonance structures here. So please keep in mind that this double bond here can also be located at the other two carbon atoms here, and that this negative charge can also be delocalized. Okay, we can draw resonance structures in which either the negative charge is located at this oxygen atom or at this oxygen atom. So of course, bidentate ligands with other donor atoms are also possible. So for instance, we can also have phosphine ligands that are bidentate. Sulfur containing ligands are also common. Okay, so now when you look at all these examples, you may have noticed that the oxygen or nitrogen donor atoms are either 2 or 3 carbon atoms apart. And that's no coincidence. So many common bidentate ligands have that feature. And the reason for that is that when the donor atoms are 2 or 3 carbon atoms apart, then these ligands can make 5-membered or 6-membered rings with a metal. And 5 and 6-membered rings are particularly stable, so that gives particularly stable coordination compounds, and chemists usually want to produce and synthesize something stable. Therefore, these kinds of ligands are particularly common in coordination chemistry. So you see here one example that uses the oxalate anion as the ligand. So here we have a tris oxalator iron minus complex, and you see that the oxalate ligands make 5-membered rings, okay, with the iron. So the iron could be considered to be the first atom, then this oxygen would be the second one, this carbon the third one, this carbon the fourth one, and this oxygen here the fifth one. And these rings are just particularly stable because we don't have a lot of ring strings. 6-membered rings are also quite stable. Anything which is smaller smaller than 5 has a significant ring strain, and everything larger than 6 also has a significant ring strain. When you have ligands in which the donor atoms are more than 3 atoms apart, then it's also possible that these donor atoms connect different metals, and then they do not bind to the same metal anymore, and you can also get different compounds like polymeric compounds. Okay, so let us have a look at a few tridentate ligands. So one common tridentate ligand is the bis ethylene triamine, also abbreviated tris ligand. So here we have just one additional ethylene group and one additional amine group in addition to the ethylene diamine unit that we have seen before. But you see again that also in this case, our donor atoms are 2 carbon atoms apart, and that's again ideal for the formation of stable chelate complexes. All right, so here we have aromatic analogs. So here we have the terpyridyl, also abbreviated terpyro. Here we have 3 pyridyl units that are linked together so that the nitrogen donor atoms can make 5-minded rings with the metal to which they would bind. Okay, now let us look at a few tetradentate ligands. So one very common tetradentate ligand is the porphyrin ligand here, in which we have 4 pyrrole units that contain 4 nitrogen donor atoms, which are separated by 4 carbon atoms. And this ligand is a cyclic ligand, which is pi overall the cyclic ligand, which is pi, which has conjugated pi bonding within it. So this kind of ligand can hold and coordinate all kinds of metals in a square planar fashion, especially metal ions that have the have a 2+ charge, because then the 2 nitrogens here and here, they will be deprotonated, okay, and that gives overall a neutral complex. So these porphyrin complexes are very important in biology. You may have encountered them in other classes, especially when you're biochemists. So, for instance, they occur in blood. So hemoglobin is a substance which contains porphyrin units that contain a particular metal in the center. You probably know which one. And hemoglobin, what is in the center of the porphyrin unit? Sorry? Iron, correct. Yeah. And oxygen can bind to that iron in that porphyrin unit, and this way oxygen is being transported in the blood to the cells. Another example is chlorophyll. Do you know which iron? Which ion is in the center of the porphyrin unit in the chlorophyll? It's magnesium 2+. Okay, so related compound here is the phthalocyanine. So here we have benzene units, which are attached to the pyrrole units here. So these molecules are often used as a dye because they also have a very intense color and are also quite stable. And the color can be tuned depending on what metal ion you actually put here in the center of the porphyrin. I see there's the chat. Oh yeah, answers also in the chat. I'm sorry that I did not see this. Yes, the answer is also correct by Christian Ruth. We have iron in the center of the porphyrin unit in the case of hemoglobin. Okay, so now let's go from the tetradentate ligands to the hexadentate ligands, which are also pretty common. So one very common hexadentate ligand is ethylene diamine tetraacetic acid, or to be more precise, the deprotonated form of that acid. And you see the molecule here. So you see here in the center, the ethylenediamine unit, but the protons have been substituted by acetyl groups. So this nitrogen here is attached to these two acetyl groups, here and here. And this nitrogen here is bound to this acetyl group here and this acetyl group over there. So overall we have 6 donor atoms here, 2 nitrogens and 4 oxygens. 1, 2, 3, 4. So these 2 nitrogens are basically 2 carbon atoms apart. You see that this oxygen, the oxygens and the nitrogen here are again also 2 carbon atoms apart, which is ideal again for the formation of 5-membered rings. So this hexadentate ligand can actually wrap around metal ions to form octahedral complexes, which are extremely stable. This is actually shown here for the example of calcium. So see how the calcium here is hexa-coordinated and surrounded by the ligand in an octahedral way. Okay, so the 6 dotted lines actually make an octahedron, as you can see. And we only have 5-membered rings between the ligand and the calcium. So because of that, these complexes have a very high stability, which enables applications for them. So for instance, you can use EDTA for water softening. So the complexate calcium 2+ very effectively. So for that reason, you can actually selectively remove calcium 2+ ions, and this way you can use EDTAs as water softeners. So the calcium 2+ is so strongly bound, it doesn't precipitate with other anions anymore. So for instance, carbonate or sulfate. All right. So now let us try to find the 4 names for coordination compounds. So first of all, we have to consider that there may be more than 1 ligand attached to a particular metal, and we indicate how many ligands we have by Greek prefixes. So if we have 2, then we use the prefix di. We have 3, we use the prefix tri. If there are 4, we use the prefix tetra. If there are 5, we use the prefix penta. There are 6, we use the prefix hexa. There are 7, we use the prefix hepta. For 8, we use octa and so forth. So in the next step, then, we look at, well, do our ligands form a complex cation or complex anion? So let us first assume we make a complex anion, and we need to name that complex anion. So the complex anion needs to have a cation, and we name that cation first. So on the second step, we number and name the ligands, and we add a suffix O to the ligand, indicating that our ligand is anionic. Our ligand must be anionic, otherwise we would not arrive at a complex anion, given that our metal ion is positive. So in the next step, you name the metal ion, and you then add the suffix "ate" to the end of the name of the metal ion. So after that, you can either add the oxidation number in Roman numerals, or you add the charge at the complex anion in in parentheses. Okay, let's practice this by one example. So how would we name this compound here? So we first realize that we have a complex anion. So the positive counter ion is named first, so that would be potassium. Note that we do not count the number of counter anions, so it's not tripotassium, but just potassium. And the next step, we number and name the ligands. So our ligand is a cyanide anion. So when a cyanide anion acts as a ligand, we remove the ending "ide" and replace it by the suffix "o." So we don't say cyanido. It sounds more elegant when we say cyano. Okay, so CN minus ion that acts as a ligand is called a cyano ligand. So how many of these do we have? Well, we have 6 of these. So the name continues with hexacyano. So after that, we need to name the metal ion and add the ending 8. So our metal is iron in this case. However, by convention, when we have anionic complexes, then we use the Latin name, if such a Latin name exists, and not the English name. So the Latin name of iron is ferrum, because the element has a Latin name, also the element symbol is named after that Latin name. Okay, so whenever you see the element symbol which doesn't fit the English name, it probably has a Latin name, and then you have to use the Latin name. In the case of iron, it's ferrum. Now you have to add the suffix "ate," but because it's difficult to pronounce, you don't say ferrumate, you say ferrate. Okay, so Latin names usually end with the ending "um," so remove the ending "um" and just add the ending "ate" to the last consonant. Therefore, in this case, the name would be ferrate. So after that, we could add the oxidation number of the iron or the charge of the complex anion in parentheses. So what would be the oxidation number? How would we determine that? Well, you see here that our complex anion has a 3- charge. So we have 6 cyanide or cyano-ligands, which have 1- charge each. So that gives negative charges. Then the question is, what needs to be the charge of the metal so that overall 3 negative charges result? What is it? I mean?
Sorry, 6 minus? Sorry, wait, that's just 3 minus.
See an answer in the chat here also? Okay, so it is actually plus 3, and that is because -6 plus 3 gives -3. So the determination of oxidation numbers is not always that straightforward, so it's actually easier just to add the charge in parentheses. That would be in this case -3. So we could either say this is a potassium hexacyanoferrate 3, whereby we put the 3 Roman numerals behind the name. And this kind of nomenclature would be called the stock system. Or we could say that this is a potassium hexacyanoferrate 3-, and the nomenclature system would then be called the Ewing Bassett system. So both types of nomenclature are equal in literature, so you should know of them both, need to be able to do them both. Awesome. All right, so let's do a few examples together. So here we have compound with formula H2PTCl6. So the PTCl6 unit makes a complex anion because it's here in bracket. So we have, in this case, protons as the cations. So what would be the name? Can anybody tell me the name? Or write the name in chat. You can also unmute yourself and speak. You will be able to hear you.
Okay. What about hydrogen as a chloroplatinate too?
Yeah, that's correct. So it's a hydrogen hexachloroplatinate. You said 2 or 4?
4, that would be 4.
4. Yeah, 4 is actually correct. So it's hydrogen hexachloroplatinate 4, or in the Ewing Bassett system, we could also call it a hydrogen hexachloroplatinate 2 minus. Actually, see, I forgot one thing here. So now we can actually hear you better. Okay. Now, why is the name like this? We have to name the cation first. So this is hydrogen. Then we have 6 chloro ligands. So we have hexachloro. The metal is platinum. So we have to give the ending 8. Now, we again remove the ending U, M, and just add 8 after the T. So that makes sorry, after the N. So that makes a platinum 8. So the oxidation number is +4. Why is that? Because the complex anion has a 2 minus charge. So if 6 chloro ligands, which are negatively charged, so 6 negative charges. So how many positive charges do we have to add to these 6 negative charges so that we arrive at 2 negative charges? Well, we have to add 4 positive charges. Okay, now let's go to this example here, which is a little bit more complicated. So me not know the name of this anion here is 203. You know the name of this anion? So that's a thiosulfate anion. It's like sulfate, but one oxygen is replaced by sulfur. So this is thiosulfate, and the name of the ligand would then be thiosulfato. So now, based on that, what would be the name of the compound? Okay, I see one answer in the chat. Potassium dithiosulfate argentate 1. That's almost correct. So potassium is certainly correct. Then the prefix di is correct, but the ending of the ligand should end with an O, so it would be thiosulfato, and then we need to call it argentate, correct? Because we have to use the Latin name of the element, silver, which is argentum. Remove the ending um, replace it by 8, and the oxidation number of the silver is +1. Why is that? Well, we have a 3- anion. So our thiosulfato ligands have a 2- charge each. So that gives 4 negative charges. So we have to ask -4 plus what is -3, and -4 plus 1 is -3. All right, so therefore this is potassium dithiosulfato argentate 1 or a potassium dithiosulfato argentate 3-. Okay, then let's go to the nomenclature of complexes that have cationic coordination spheres or complex cations. The rules in this case are similar. We first number and name the ligands. Then we determine the name of the metal and either place the oxidation number or the charge in parentheses behind the name of the metal. So in this case, the metal doesn't get a suffix, and we always use the English name of the metal. And lastly, we name the counter anion. So here's one example. So in this case, we have 2 amine ligands, NH3. So note that when an ammonia molecule acts as a ligand, it's called an amine ligand. Okay, please remember that you have to spell amine with 2 M, yeah, and not with 1 M, because in this case, amine comes from ammonia. Yeah, please also don't do this wrong in an exam, because I will subtract points if it's spelled not correct. So how many of these ligands will there be? Well, there are 2. So it's a diamine. The next we have to name the metal. So this is silver. Then we need to state the oxidation number. So you see that we have here a 1+ charge, it's a complex cation. The amine ligands are neutral because the ammonia molecules from which the ligands are derived are neutral. So therefore, the silver must have 1 positive charge and the oxidation number must be +1. So lastly, we name the counter anion, which is in this case chloride. So overall, this is a diamine silver 1 chloride or a diamine silver 1+ chloride in the urine Bassett system. All right, so let's do 2 exercises with this as well. So can anybody name this coordination compound here? PTNH3,4Cl2. Everybody is invited to make suggestions.
Would it be tetradentate 2?
Yeah, it's tetraamine, platinum, 2 chloride. Yeah? Yeah. The anion we also need to name. Please again make sure that you do not count the number of counter ions. So don't say it's a dichloride, it's just a chloride. Okay, so we have tetraamine, platinum, 2 chloride, or tetraamine, platinum, 2+ chloride. Good. Let's go to the second example. NiH2O6Cl2. How would we name that?
Is a aqua nickel 2 chloride.
Yes, so this is a hexa aqua nickel 2 chloride or hexa aqua nickel 2 plus chloride. So notice that when we have water as a ligand, it's not called water anymore, but aqua. So of course there are many ligands. I would like you to memorize those that we are using here in class, so that you know at least some of them out of the top of your head. Of course, there are many more than we are actually using. All right, then of course it can be that there are compounds that have a complex cation, any complex anion. In this case, we just combine the rules that we have learned before. So we just named complex cation first and the complex anion last. So what would be the name of this compound here? This complex cation we already encountered. So this is a diamine silver 1. Then we named the anion, which we also encountered previously already, which is a hexacyanoferrate 3. So it's a diamine silver 1 hexacyanoferrate 3, or we could also call it diamine silver 1 plus hexacyanoferrate 3 minus. Okay, a few more things to consider. We can have more than just one type of ligand. So in this case, we have to decide, well, in which order do we name the ligands? So in this case, we order them according to the alphabet. So here's just an example. Here we have a cobalt NH3,4Cl2 NO3. So we see that amine comes in the alphabet before chloro. Therefore, we have to name the amine ligands before the chloro ligands. So therefore, this would be a tetraamine dichloro cobalt. And in this case, the cobalt has the oxidation state +3 because the amine ligands are neutral. The chloro ligands have a 1- charge. And the complex cation has a 1+ charge because the nitrate anion has a 1- charge. So therefore we have -2 +3, which gives +1 in this case. So it's a tetraamine dichlorocobalt 3 nitrate or a tetraamine dichlorocobalt 2+ nitrate. So here one more example in which we have even 4 different ligands: an amine ligand, a bromo ligand, a chloro ligand, and an aqua ligand. So the amine ligand comes first. Then there comes the aqua ligand. Next comes the bromo ligand and then the chloro ligand. So overall, this will be amine, aqua, bromo, chloro, platinum. For sulfate, the oxidation number is 4 because we have sulfate as an anion, which is a 2- charge, so we must have a 2+ charge at the complex cation. So we have 2 ligands which have -1 charge, the bromo ligand and the chloro ligand. So therefore, the equation is -2 plus what gives +2, and -2 plus 4 gives +2, and therefore the oxidation number of the platinum is +4. So we could also name aqua amine bromo chloro platinum 2+ because the charge of the complex cation is 2+. All right, then it can also be that a ligand is a more complex molecule. So in this case, And this more complex molecule contains prefixes in itself. And in this case, we place parentheses around that more complex ligand. In order to number the more complex ligands, we use somewhat different prefixes. So we use bis instead of di, we use tris instead of tri, we use tetrakis instead of tetra, pentakis instead of penta, and so on. So one example is this complex here, where we have an ethylene diamine ligand, or actually two of them. So the ethylene diamine is a more complex chelating ligand. It already contains the prefix di. So in order to avoid ambiguity in the name, we put the ethylene diamine parentheses and change the prefix in front of the ethylene diamine. In this case, from di to bis, because we have two of them. So we have two chloroligands. So we have to consider the alphabetic order of the ligands as well. So C comes in the alphabet before E. So we have a dichloro bis ethylene diamine cobalt, and again the covalent oxidation state +3, so it's a cobalt 3. Right? Dichloro bis ethylene diamine cobalt 3. We also say it's a dichloro bis ethylene diamine cobalt 1+. Okay, so last but not least, it can be that a ligand is not terminal, but it's bridging. So when the ligand is bridging, then it gets a prefix mu. And ligands that are bridging are being named first, and all other rules apply as they have been used before. So let us do one example. So we have here a complex with two cobalts and an NH2 ligand, which is bridging. This ligand is actually called an amido ligand, amido. It's an NH2 minus unit. And here this ligand is called an hydroxyl ligand. So these are both bridging, so they are being named first. And we have to apply now the alphabetic order also. Therefore, we have to name the amido ligand first. So it's a mu amido, mu hydroxyl. So after we've named these ligands, we name the fragments that are bridged according to the rules that we have learned. So such a unit here would be called tetraamine cobalt. And we have now two of them. And both units are again more complex, so we use the prefix bis in front of them. So overall, this would be a mu amido, mu hydroxyl bis tetraamine cobalt. So the oxidation number of the cobalt would be placed behind. So in this case, it's the oxidation number +3. Why is it +3? You see that this complex cation has 4+ charge. We have these neutral amine ligands here, and these anionic amido and hydroxyl ligands respectively. So they have both 1- charge each. So therefore, we have to think about what do we have to add to -2 to arrive at 4+. So -2 + 6 gives +4. But now we have two cobalts, so we have to distribute these 6 positive charges over 2 cobalts, and therefore each cobalt gets a 3+ charge, and therefore the oxidation number of the cobalt is +3. Okay, alternatively, we could call this also mu amido, mu hydroxyl bis tetraamine cobalt 4+, because 4+ charges of this cation. All right, so let's stop at this point here.